Okay, so what about other molecules? So for example, this one that I'm drawing right here, okay, this is formaldehyde. Formaldehyde, okay. So maybe some of you have heard of formaldehyde before, right? It's that embalming agent that you put in all those, random, weird little biological things that all you people could tell me more about. So when we have a complicated molecule like this, we kind of have to inspect all of the regions of the molecule to see what we expect would be polar. Okay. Now carbon and hydrogen is tempting because we see hydrogen is here and carbon is here. But based on that electronegativity scale, if I go back to that, carbon's 2.5 and hydrogen's 2.1. There's not a lot of polarity difference between carbon and hydrogen. Carbon and hydrogen are mostly covalent. They're mostly sharing equally. Okay? But now if you look at carbon and oxygen, that's big enough. So 1.0, it puts it right on the kind of the border there. But carbon and oxygen, that's a big enough difference to be polar. Okay? And you also notice here that in this Lewis structure, there's a double bond between carbon and oxygen. We'll talk about how we make double bonds soon. We also notice that oxygen has lone pairs. We'll talk about how we can predict that, how we can come up with that. Okay? And so what this means now in our dipole moment, all right, there is a strong dipole moment between carbon and these oxygens. This carbon is electropositive. The oxygens, not only is oxygen electronegative, but it has those free lone pairs. So when we draw this dipole moment, right, we make a positive sign, okay, and then we draw an arrow towards the negative end. And we can also use these partial signs, partially positive, partially negative. Okay, so here's an example for you. Draw the dipole moment for each of the following molecules. All right, so let's do it. Okay, so the first one that I'm gonna work on is, let's work on the ammonia. All right, and here we can see hydrogen and nitrogen. And hydrogen and nitrogen is fairly significant, okay, right? 2.1 and 3.0. And I don't want you to memorize these numbers. What I want you to kind of start to recognize is the trends. Like one of the trends we just uncovered, carbon and hydrogen, not so polar. Hydrogen and nitrogen, it's right on the border, so it counts. It's on the border enough that it is polar. Furthermore, nitrogen has that free lone pair of electrons, right, making it somewhat negative. So if I pick on this hydrogen, I know that this hydrogen is somewhat positive, okay? And it, ooh, that was weird. And then it points to this negatively charged nitrogen. Well, look, there's another dipole moment in this molecule, right? So there's one right here as well, okay? Also, there's another one right here. So what is the net effect of that? Well, as you can see, what maybe you might guess is these two right here will cancel each other out. Okay? They will cancel because they're equal and opposite. However, this one does not get canceled because there's not an opposing dipole moment. And so I'll draw in red the grand total dipole moment, if you will, okay? And so that is going to go right through the center of this molecule, something like that, okay? What about this CCl3H? Okay, what about this compound? Well, carbon and hydrogen, not so much, okay? But carbon and chlorine, there is a fairly big difference, okay? And so now it looks like this. Okay, we've got a dipole moment that points out that way. We've got a dipole moment that points out that way. And we've got another one that points out that way. And it's the same thing that's going on with this NH3. Okay, these equal and opposite dipole moments cancel each other out. And so what we're left with is a dipole moment that goes from hydrogen through carbon through chlorine, which makes good sense because hydrogen is also somewhat positive, taking us right through the center of the molecule. Okay. So now what about this SF6? Well, here's sulfur and here's fluorine, and it definitely looks like they're very close to each other, the sulfur and the fluorine. But look, because fluorine is so electronegative, right? It's hugely electronegative. That's a difference of 1.5. A sulfur and fluorine bond is definitely polar covalent. So now we know that there's going to be a positive near the sulfur and there's going to be a negative that points near the fluorine. Okay, for that one. But look, there's one there. There's one there. There's one there. There's one there. And there's one there. So even though the sulfur-fluorine bond is polar covalent, there is no dipole moment for SF6 because they all cancel each other out. Okay? So that's also really important.